Hi, I am Gion, a student at Sun Yat-sen University, and I am excited to introduce HumanRefiner. First, please take a look at the two rows of images. The top four were generated by the state-of-the-art text-to-image model SDXL. As you can see, even with such a large parameter scale, errors occur in the positioning, number, and shape of limbs. The four images below showcase the results generated by my improved model, which I will now present. Why did I choose this topic? There are two primary motivations. First, generative models are evolving rapidly, with new advancements like SDXL, DALL-E3, and Deep Fluid emerging. These models use increasingly large training datasets and show remarkable performance in general domains, yet they fail to address the challenges of human body generation. Second, although there are existing works focused on human generation, such as HumanSD, ControlNet, and T2I adapter, their results are unsatisfactory. Most also rely on additional conditional inputs, limiting their generalization and applicability. Next, let me introduce some key concepts. All the generation in this work is based on diffusion models. The most classic work in this area is latent diffusion, shown here. Its principle involves progressively adding noise to an image until it becomes a normal distribution, and then using a U-net to learn the denoising process, thereby learning the data distribution of the image. The novelty lies in employing a variational autoencoder, VAE, to project the image from pixel space to latent space, significantly improving training efficiency and performance. In conditional controlled diffusion, the key mechanism is cross-attention computation within the U-net. Original latent diffusion uses CLIP's text encoder to extract textual features, while methods like T2I adapter employ lightweight networks to extract features such as pose, line drawings, or depth, which are then injected into the generation process via cross-attention to control the output. This task faces several challenges. First, models like HumanSD are built on SD 1.5, meaning that once new models are released, they become obsolete and cannot be used interchangeably. Additionally, many human generation models, such as Hyperhuman, require extra inputs, increasing the complexity of the structure and inference time. A core issue is that existing datasets lack annotations for detailed limb features. Shown here is one of the most related works from CVPR, but it has a relatively small dataset and focuses only on real human images. To address this, I first tackled the data problem by developing a synthetic abnormal limb dataset called AbHuman. The textual prompts were sourced from LAION and HumanArt, and some were generated using ChatGPT. SDXL was used to generate the images, which were then annotated by trained experts who provided fine-grained bounding box annotations for limb anomalies. We annotated a total of 18 categories, and as shown in the table, hands remain the most error-prone part, often humorously referred to as the six-fingered AI. Compared to other works, AbHuman provides more fine-grained annotations and richer information. Using this dataset, I implemented several modules. First is the Anomaly Scorer, an MLP regression network that addresses the lack of standards for evaluating the quality of limb generation. Next is the Anomaly Detector, an object detection network that efficiently locates and identifies abnormal limbs. Based on these modules, I developed HumanRefiner, a framework that can self-diagnose anomalies and progressively refine from coarse to fine. The Anomaly Scorer's score serves as guidance for training the model. After the initial generation, there are usually issues with limb positioning and number, which are resolved first using a pose adapter. Then, the anomaly detector identifies areas with shape issues, and the diffusion model is used for a secondary redraw, further correcting the anomalies. In quantitative experiments, my model demonstrated strong performance in reducing anomalies, maintaining content relevance, and improving image quality. In qualitative experiments, the results showed significant visual improvements. For more results and details, please refer to the paper and visit our website.